I'm Dustin Mackey. I'm a software engineer with this large group that we have at UVA. Been with them for a long time. Today I'm going to talk about the Net.Science project. But before we do that, I want Chris and Ravi to introduce themselves, and Chris may want to say something about the project.
Hi, this is Ravi. My training is in computer science. As far as this project is concerned, I'm more like a cheerleader. I know I present stuff, but most of the work is done by Chris, Dustin, and others. Thanks.
I'm Chris Kuhlman, and Ravi typically undersells what he does, just like he did there. He does a lot on this project. My background is computer science. A brief intro about the project overall is that this is an NSF-funded project. It has as its major deliverable to produce and make available this cyber infrastructure for network science called Net.Science. And we're going to demo it today. And this thing is a living infrastructure. And what it means for you is that if you see some feature that you would like to have that's missing, or some feature that could be extended to help with your work, please be thinking about these sorts of things and let us know about them, whether we have time at the end of this meeting or at some other point, because Dustin and Ravi and I are around and we would like your feedback.
So I'm just going to give a brief overview of the system itself and the basic interaction means. And then Chris and Ravi are going to go into some more details. Ravi will talk about structural analysis of network graphs. And Chris, I think, will talk about contagion simulations. So I'm just going to go quickly over this, and I'll show a brief demo and then get them onto their pieces. So this is the basic system at its kind of no bells, no whistles from that perspective. So we have an application that's represented by this blue box. It's a web application, and that's the URL for this application. Anybody can go and see it and sign up. We have a file service where files can be uploaded and downloaded from. And then we have a job service, which launches jobs on our computational infrastructure, in this case, the cluster at UVA called Rivana. And the inputs for those jobs come from this file service, and the output of those jobs also goes back to this file service. So everything is managed there, and you can upload new networks that you create or download the results of analysis or things like that from that system. Now, I just described it as the interface for Net.Science, but similarly, there's an API behind all of this. So using a HTTP API or the command line or a Python client library that is in development right now, you can do all these exact same things, write your own applications or do your own more complicated analysis, kind of making small workflows of different tasks that are in the system, different jobs that are in the system. So we have these core services that I just explained a couple of them. The user service is what authenticates and grants permissions, all of that kind of basic user stuff. We have the file service where we're storing files, and the job service to launch jobs and run them to completion. So first, I'll talk briefly about this file service and what it does. So in here, we have basically your traditional directory structure, a hierarchical structure of folders. And inside of there, we can put files of any type. We have enumerated a number of different file types that can have special properties, and I'll talk about them. But what you'll see in Net.Science specifically is that you have a home directory that you can browse to, and then you can organize that however you want. And we have a resources folder, which is where we put publicly shared networks and things like that. There are only a limited number of publicly shared networks at the moment, but we're hoping to get up into thousands of networks that we will download from other places and make available for your research or analysis or playing around, whatever you want to do with them. You'll see that in a minute in the demo. One key thing to note here is that we're trying to do reproducible science. So when we put files in the system, they're not modifiable. If you want, you can, of course, delete a file and put a new version of that file in there, but the files themselves can't be modified. And this is to make the science reproducible. There's a bunch of properties of these files, such as the MD5 hash of any individual file, so that you can verify that the file you've downloaded or upload by running an MD5 checksum against that. You can verify that that operation is completed properly. Generally, you don't need to do that kind of thing. We have a number of different file types in the system, and these file types, they're more than just enumerating the different files we have. When we put files into the system, based on the type of file that is in the system, we can know what types of things we can do against them, meaning these are valid inputs to specific types of jobs, but also so that we can run validation and metadata extraction from those files automatically. And you'll see this in just a minute. Well, in fact, you can see it on the right. when we put a file into the system, in the case of a network file type, we automatically run some structural analysis properties, and this is what I call discovered metadata. So this is metadata that we automatically extract from any one file, and you'll see some examples of that on the right-hand side here. All these nodes and edges, these are just by virtue of putting this file into the system, we automatically analyze that network, extract these properties, and store them automatically to make them searchable or viewable or things like that. But you can also add your own custom properties in, arbitrary properties that you want to add in. That's what you'll see, this custom prop on the right side. And then that property becomes something that's searchable. We have folders and containers, which are just what you would expect them to be. A folder is just a holder of other files, but we can also have specialized containers that are named containers that will have particular properties. For example, we could have a folder that's expected to have one text file and one JSON file in them. Not too important for today's discussion, but it's that kind of capability that's in there. One important piece that we have is provenance. So any file that's in the system, we can tell where it came from, except the point where it came into the system. So when you first upload a file into the system, the provenance of that file is just user provided. But when we run a job and that job itself produces some output, we track that as provenance, that this is the job that was ran. This is where the job was ran. These were the inputs and input files to that job. And so in that way, you can walk all the way up a provenance chain to find where a file first came into the system and all the analysis that happened on it. Permissions, they're the kind of typical permissions that you expect, read and write permissions. There's also a specialized thing called compute privileges, which allow you to grant access to a file or be granted access to a file so that you can use it in computations, but you can't download that file itself. And this is for some files that we have that we're not allowed to publicly share. So we have some populations, for example, for our simulations that were produced with commercial input data, and we're not allowed to release them publicly, but we want that people to be able to compute against them, run simulations that use these populations. So this compute privilege is a specialized permissions to allow that. And then finally, we have transformations. So a file can be in one format, and we can define transformations of that file to other formats so that if a particular type of job that you want to run, we can transform files on the fly from one file type to another file type to run that job. So this is just an example of using the command line tools to look at a particular folder. And what you see in here is the list of files in my home directory, home dmackie, and the file names on the left, and then the ID, size, etc. And one thing to note about this is these files can either be accessed by their full path. So like this first file would be home dmackie test file.txt, or it can be accessed by ID. So that way, if you're submitting a job and then the file gets moved, or you shared a file and it gets moved somewhere else, that file is still accessible by ID, so it doesn't mess up any of those linking properties. Here's just a quick look at a single file and some of these properties that I'm talking about. And we'll see some more example of these when we get to UI in a moment. So we're looking at a file called test.pun.graph. And on the left, you'll see a provenance section, and that's saying this was run by the site job service I was referring to. The reference ID is the job ID, and these were the input parameters to that job. So we know where this file came from. A bunch of other properties that I won't go into. And then this auto metadata section, you'll see here, average edge between the centrality. These are the structural analysis properties that we automatically calculated. And then there's a variety of other properties in there that aren't as important at the moment. That's the basic file service. Now we'll talk about jobs. So jobs are individual atomic tasks that can be run. We probably won't go into a lot of detail on this thing, but what you should know is that we define a job, and that software for that job, the code itself, is stored in a container, like a Docker container, although in this case we're using Singularity containers. And inside of those containers, we have some configuration files that tell the system what is the input schema, so valid input parameters to this job, what are the input files that are valid for this job, what are the output files, and what are the required resources. These are all defined as part of these containers and imported into the system. And then any one of these containers contain a number of atomic jobs, and these get exposed to the user so that we can submit these jobs. So again, the input parameters and files are included in there, output files and output data. Any one of these jobs can produce either output files or output data or both. And you'll see on the right, it says output files, home, SSRavi, on a full path. This would be an example of an output file. So this job that was run generated a file, but it also has output data, which is just an integer in this case. So Depending on the type of job, some jobs just produce a scalar value as the output. That might just be output data, or they can produce file output, or both. And so various jobs will do this kind of thing. Any of these jobs will have a number of states, from user queued being a state where the job has been submitted to the system and accepted by the system, but it hasn't been pushed off to a particular compute resource yet. Queued is when that job has been pushed off to a particular compute resource, and running, completed, failed are pretty obvious. And you see on the right, you can see standard out, standard error, if there were any. Those are all other properties that you can view of this particular job. There's the facility in the UI to search for these jobs, and scaling. We're not going to talk about that right now, but basically that is saying we can configure these jobs to scale up based on the input parameters and input files to scale the job to the resources it needs. So when we submit a job, this is the basic process the job goes through. And the idea here is that some of these jobs could be long running jobs, and we don't want them to fail for something stupid, basically, later after the job has sat in queue, waited to run, and then finally started running, and then an hour in, it fails. So we try to catch simple errors before the job is submitted. So what you see here, we submit a job. First, we validate the user has permissions to run that job. We validate the input parameters, match that of the input schema. Then we retrieve the input file metadata and validate the input files are accessible and of the appropriate type for this particular job. And after those have passed, we put the job in a user queued state and return the job ID, and then it runs through the states that we mentioned. So that's the basic idea of the system from my slide perspective. Anybody can register. You go to Net.Science, click on register, fill out the form. One thing to note is that your username that you use is going to be visible to other users of the system if you share files or anything like that. So you don't want to use your email address as your username. Keep your username separate. But this is pretty standard registration process. Now I'll show you very quickly the user interface itself. So this files, what I was referring to before, you have a home directory and a resources directory. Let's look quickly at home directory. And then this is just a browser like any other, so I can click around, see files. If I want to, let's go look at a particular graph. So here's a graph I created a half hour ago. This is just a random graph. So if I click on this graph, I can see some of the properties on the side here, the basic properties, those metadata properties we were referring to, provenance data, but we can also click on the graph directly to see it. So again, this is the same data that we're seeing on the side, but you can also see the data itself, depending on the size of the data, the metadata, all that information we were just talking about. And here you could add a property if you wanted. Provenance information. And depending on the size of the graph, in the case of a graph, you might be able to see a visualization too. We have some caps on this because this is a purely client-side visualization. So if the graph gets too large, the browser will have trouble rendering it. But this also includes the ability to change to some different layouts. This list of possible layouts is also dependent on the size of the graph. So there's other properties to search for files within here, to refresh that listing, create a folder, or upload a file. You'll see some more demonstrations of some of these various things as Ravi and Chris go through their presentation, so I'm not going into too much depth here. Finally, we have this job section, and if you go here, what you're going to see is a list of the jobs that were completed. So these are all the jobs that I have run as this test user, and I can click on any one of them, and on the right, you'll see the output files. I can see the standard output of that file. If I click on this file, it's going to take me straight to that. Always choose this one that is invalid for some reason. Typically, you can click on these links and go to them. And then you can also see the input parameters for those jobs. To launch a job, on the other hand, you click on this plus button, and that's going to list all of the different types of jobs that exist within the system. And there are currently 388 that I see. There are actually more than that in there, but this is based on permissions, and we have some development things in here. But you'll see all of these different types of jobs in here. What you're seeing now is mostly all of the Stanford Snap library methods, the CSonnet, our simulation code, and some visualizers of graphs, as well as outputs of simulations. So if I choose one of these, I can search for, say, generate a random GNM. So this is a graph generator. I select that, and then it's just a simple web form that you fill out. So I might say I want to generate a graph with 2,000 edges. I want it to be directional. I want it to have 100 nodes. Because this is directional, I want this to be a PN graph. And then you would select the output location, what you want to name it. So we'll call this GNM 100 2000 PN graph. Hopefully that doesn't already exist. It submits the job, takes me back to this page of my job listing. And you can see that job already went to user queued and then into the queued state. And then depending on the load on the machine, it will start running, which it's already done. And then it runs to completion. And then once it's run to completion, I can go view those files by either clicking on that guy or going to my home directory. This is the graph that we just built, and then the visualization of that and that information. So that is the super quick overview of the system. Again, basically what we're doing is putting files into the system and running jobs against them. And that's the major interaction mean for the whole system. Of course, there's a lot of different jobs that you can do, and Ravi and Chris will talk about them more. So I'm going to stop here and pass this over to Ravi.
Thank you. So in 15 minutes or so, I'll show you 3 simple demos dealing with structural analysis of networks. I think people are very interested in visualizing networks. One of the things that Dustin showed you was the browser-based visualization, but you can also do other things. See, we can read these instructions as to how to do this, but let me go straight to the system itself and show you how to do this. First of all, I need to log into the system. So let me do that. So what I'm going to show you is to visualize networks, as I said. Now, Dustin showed you how to generate a graph. I did that yesterday. And so I'll meet on a job so that I can actually visualize this. Okay, I'll show you. As Dustin said, in order to start a job, you click on this plus button, okay, as part of jobs. I want to visualize a graph. So in the search box, I just type viz. It gives you this possibility of which graph to visualize. So I'll select that. It gives you various options. Okay, this is much more extensive than what the browser side visualization does. So I can choose the layout algorithm. You can see that there are many possibilities. For today, I'll go for layout. Okay, at the moment, I'll leave out the contract to begin with. So you'll see the entire network. We'll see what the contract option does in a second. The graph is not directed. Let's say the clustering is based on community multi-level. Okay, again, there are many choices, many possibilities. The display color, okay, let's say I want to choose blue. And let's say I want to make it 1,000 by 1,000 output height, output width, and the output type is PDF. And the nodes are going to be scaled according to degree, meaning that the circle associated with the node is going to be larger, the larger the degree of the node. Let's say at this point, I don't want to drop isolates, so I need to specify the file. Let me select this file. What I did was I created a directory called July demo. So I'll go into that directory. Let's say I want to visualize this particular graph. It's a graph, it's a random graph with 100 nodes and 300 edges. So I'll select that. The input file has been selected. The output container, again, I'll choose the same demo directory. Okay, the container is a directory. I'll select that. And when I name the output, I'll use this J12 prefix so that this file is distinct from the other ones. So this is J12 visualization, random graph with 100 nodes and 300 edges. So now that I've specified everything, I can actually submit this job. So let me say submit. You notice that this green box tells me that the job is being submitted. It'll show me that the job is actually running. Let me show you another facility that the system has. While this is going on, what I can do is to try another job. Let me run this, again, the visualization with the contraction facility that I showed you. So I'll select this. Once again, it is auto. I'll keep everything the same. The color is blue. I want to contract. What the contraction does is that it takes certain nodes of the graph and contracts them to a single node so that for large graphs, you can visualize them slightly better if you don't have too many nodes. And again, let's say it's 1,000 by 1,000 PDF. And it is, again, the scaling is by node degree. Let's say we also want to drop isolate. There are no isolates in this particular graph, but you can actually choose that. Once again, the file that I want to select is the same as before. I'll go into this directory. I want to choose this file, which is a random 100, 300, which I generated yesterday. On the output file name, I'll call it J12 for July 12, contracted version of RAND 100, 300. Okay, so that's the output file name. So this is a contracted version. The original was the uncontracted version. It didn't specify something. If I specified everything, the submit button will be on. Let's say I didn't specify the folder. So the folder that I need is, again, the July 12 demo. So now that everything is complete, I can submit this job. Let's see what is running. Okay, so the previous job, the graph visualization completed. If I click on that, so let's see. So this is the file that got generated. See, notice the J12, this is a visualization, this data, that the data is a PDF file. This is exactly the visualization of that particular graph. This is what I have on my slide. So random network with 100 nodes and 300 edges. And when I contract it, this is the display I get. Again, this can vary depending upon what options I chose. Let's see, the other part is completed. This is a contraction one that's also complete. So let me click on that. So here is the output file for it. Okay, so if I look at the data, this is a little bit bigger. I had to compress this so that I could fit it on my slide, but this is a compressed representation. So this is about visualization. You have a lot of flexibility in doing this. I want to talk about structural properties also. Let me go to user home. I want to talk about some structural properties as well. There are scalar structural properties which are stored as part of metadata. So for example, the diameter of the graph, the number of nodes in the graph, number of edges in the graph, and so on, the maximum node degree. These are all part of metadata. But there are other properties like K-code, which are not single numbers. It's like a table of numbers, a vector of numbers, if you like. Those are things that we need to compute using appropriate jobs. And that's what I'm going to show you. In particular, I'll show you K-code. Since some of you may not be familiar with what a K-code is, I'll just go through a quick definition. K-code is nothing but the largest subgraph in which every node has degree at least k. You get the K-code by starting with the original graph and removing nodes whose degree is less than k. Okay, just want to have nodes whose degree is greater than or equal to k. So just start removing everything that is degree less than k. So in this particular example, let's say I start with this. If I look for a one core, the one core means that every node must have a degree of at least 1. Notice that in this graph, everybody has a degree of at least 1. So this is one core as all the nodes in it. There are 8 nodes, so it is all. If I want a 2 core, that means that I should start deleting nodes of degree 1. So if I delete V, everything else has degree of at least 2. So the 2 core is all the nodes except V. Now, something interesting happens when I try the 3 core. 3 core means I need to delete nodes of degree 1 and 2. When I delete this node, nothing happens to you. But this is degree 2, I need to delete that. This is degree 2, I need to delete that. I need to delete this. So when I delete B, notice that the degree of A comes down to 2. I need to delete that too. When I delete A, again, I'll end up deleting the whole thing. So in other words, the 3 core for this particular graph is the empty set. There are no nodes in the 3 core. So if I were to show you a K-core distribution, the K-core distribution is a table that has, for each value of K, the number of nodes in the K-core. As we saw, the 1 core has 8 nodes in it. The 2 core has 7 nodes, okay, all except V. But when I go to the 3rd core, that is empty. Cores are very useful in simulations because these are dense part of the graph. But if you start the seed nodes, if you start a simulation by setting those nodes as a starting in the initial configuration, then the contagion will spread more. So K-core is important for many reasons. Okay, I'll show you how to compute the K-core distribution using Net.Science. Okay, once again, you can read these instructions, but it'll be simpler to go to the system and start there. So again, I need to run a job in order to compute the K-core. I'll start this. What I need is K-core. You have to be careful about this autocorrection. You don't want score, you really want K-core. It shows you some possibilities. I want core, it returns the number of each core. This is a number of nodes in this core, so that's what I want to select. Okay, this is K-core nodes. Any graph is stored as an edge list. Each edge has 2 endpoints. One of them is called the source, the other is called the destination. Okay, let's say the destination column number is 1, the source column number is 0. The input file that I want, let's say I choose a graph from one of the available graphs in the system. So this is part of the resources. There is Net.Science. As part of this, in workshop V1, we have this JAS network. So I'll choose that. That's an interesting property, as you'll see. So I'll select the JAS network. I want to store the output of this K-core distribution in my regular directory. I'll go into this and use this July 12 demo directory. That's what I want the result to be stored. This is a K-core distribution. So I'll call it J12 K-core Jazz. So there's a K-core distribution for the Jazz network. So I specified everything. I can submit this. Okay, once again, the job has been successfully submitted. It is running right now. It is queued. But just like cooking shows, let me just go and show you the result of this in the July 12 demo. Okay, so it looks like this is completed. A few seconds ago, it is completed. So we can actually take a look at this. The data shows me that the zero core is 198 nodes and so on. The largest core is 29. So this is a K value, and this is indeed the number of nodes in that K core. Getting back to my slides, I want to show you something interesting about this. So what I did was, instead of showing you all the values, I just chose some K values and show you the core size so that I can fit this on a slide. As K increases, the number of nodes in the K core decreases, meaning that that's something to be expected. The largest K core value is 29, and there's 30 nodes in it. Yet these 30 nodes, each of them has a degree of at least 29. So what this means is that these 30 nodes form a complete graph or a clique in the Jazz network. So this is an interesting observation about this. Okay, you can get such things. One of the other things that I want to show you is the plotting capabilities of the system. In particular, we'll take this K-core distribution and generate a plot. We can actually plot this, as I said. I want to run a job. I want to plot the K-core distribution. And that's also done by running a job. What I want to do is to plot. It has many options. The one that I want to plot is the K-core node distribution. That's what this is. I'll select that. It is a plot. So the output type can be PNG, or let's say I'll choose PDF. The file that I want to do this on, plot my K-core distribution, which is as part of this directory. This is exactly what I want to plot. So that's a file that I want to choose. And let's say the output file name is J12 plot K-core Jazz. I've chosen the file to be plotted, okay, and that is exactly the K-core Jazz. And where I want this to be stored is indeed this directory. I need to specify the path for this. So one of the neat things is that unless I specify everything, the submit button won't come on. So let me submit this. And going back to my slides, you can actually see that the plot looks like this. It starts with about 198 nodes with a zero core. The largest possible core is 29. And afterwards, it is zero. That's what the plot looks like. You can actually see that this is still running, takes a little time. And one of the other things that I wanted to show you is that as part of this directory, I generated a large graph. And here is a graph that I generated yesterday. This is a scale-free graph with 10 million nodes in it. And I did a degree distribution for it. So if I look at the degree distribution for this is what it looks like. It's a scale-free graph on a log-log plot. If I plot the degree against the number of nodes, that should look like a straight line, and that's exactly what it is. So I just wanted to show you that indeed the system can generate and handle large graphs. So in this particular case, this graph is 10 million nodes. Thank you.
Okay, so what we're going to do is look at another task in the system called Net.Science. And so we'll look at a couple of slides to begin with, just to get us all on the same page, and then we'll go back to the cyber infrastructure and run some calculations. This section is on contagion dynamics on networks. And so what do we mean by that? A couple of elements here for the inputs are the graph itself. This is a 5-node graph. It's a star with a hub node, node 0 in the middle. There's a state transition model, which gives the states that these nodes can be in. So state S is red, I is green, and R is blue. And in addition to these states, it denotes the transitions that can be made by these nodes in moving from one state to another. So this model is an SIR model. We'll be looking at it in the simulations. And so this is typically an epidemic model. S stands for susceptible, I stands for infected, R stands for recovered. But in fact, this epidemic model is used in all sorts of different domains, like, for example, the spread of computer viruses and the spread of social contagions like information. So it's a much more general model, or used in a wider range of applications than just epidemics, disease spread. So when we have these two elements combined, what we're after is computing a series of state transitions. So here in the graphic, we have the same 5-node graph, And now 3 of the nodes are red and 2 are green. And so the 2 green nodes are infectious and they can infect other nodes. And in fact, that's what happens at the next time step indicated by this magenta arrow. At the next time step, all the states of the nodes are the same except for the center node. It went from red to green, which means it went from the susceptible state to the infectious state. Okay, so this is one state transition. And you can look at it as this is the state of the system where 2 nodes are infected at some given day. And then on the next day, instead of 2 nodes being infected, there are 3. And so then you can generate plots like the one at the bottom where time is on the x-axis, and we might consider time in days. And on the y-axis is the number of nodes in the graph. And this graph could represent a population, let's say Washington, D.C. or Miami, Florida, etc. And so these would be the number of nodes, in this case, state I, that are infected as a function of time. And these vertical bars here indicate plus or minus 1 standard deviation. Okay, so this is the kind of thing we are interested in here. And we want to run these types of computations on the right, given these types of inputs on the left. And this set of slides, all these sets of slides will be made available to you. As I said before, we're just looking at one SIR model, but there's a number of different demos in this slide deck for different types of models. And if you're interested, you can run those at a later point. So give a high-level view of what we're going to do here is first, we're going to specify a network. We're going to use a network that's already in the system. Then we're going to run simulations. Then we're going to extract particular data from the raw output file from the simulations. And then we're going to use that extracted data to generate some plots. And incidentally, I forgot to mention, there's 3 folks on this call, Tanvir, Aparna, and Lucas. And these folks are postdocs, PhD students, and undergrad students. And there's a lot of students working on this. Aparna, for example, wrote the C-Sonnet simulator code. And a number of students work on all different kinds of pieces of this overall cyber infrastructure. This is just what I said before about multiple demos. And this is just more of these example transitions. So from this graphic right in the middle, what we're saying at the next time step, the node in the center goes from the susceptible to the infectious state, and one of the infectious nodes becomes recovered. So it transitions from green to blue, okay, and so on. Here's a small description of some of these transitions. But we're going to move to the demo now. And basically, we're going to use a small network so that the simulations run quickly, only 885 nodes. Our base case is when the edge probability of infection for an edge that connects a susceptible person to an infectious person, the probability of the infectious person infecting the susceptible person is going to be 0.1. And the duration of infectiousness for a given node that becomes infected is 3 days. Then we'll look at 2 variants of this. In one case, we'll keep the probability of transmission the same, but we'll reduce the number of days that a node is infectious. And in the second case, we'll keep the number of days of infectiousness the same as in our base case, which is 3 days, and we'll lower the probability of infectious transmission. And we'll look at the effect of that. In all of the simulations, we'll seed it or start the initial state such that 50 nodes are randomly chosen to be in the infectious state, all other nodes being susceptible. Okay, so now we'll go to the demo. We're going to come here and we're going to start a new job just like Ravi did before. And since the simulation code is C-Sonnet, we'll put that in and then different choices come up. So the first one we're going to do is run a simulation. So we're going to select that. The input file, we're going to go back to this collection of files that I think Dustin mentioned before about networks that are already in the system. And we're going to go into here and we're going to pick this friendship network. And that's our network that we're going to operate on. Here, there's behavior models, there's threshold, SEIR, and SIR models. And Aparna has expanded this list. And so we'll be adding those new models in the near future to this cyber infrastructure. So this is an example of how these different tasks can evolve in time in adding new capabilities, and relates to the point we made earlier about if there's something you would like to see in this system and it's not there, let us know. So we're going to take an SIR model. Right now, we only have the model where it's a fixed infectious duration. So just like on the slides, the edge probability of transmission is 1 and the infectious duration is 3. Since this is a stochastic model, because this is the probability that an infectious node makes a susceptible node now infectious, we have to seed the computations for the random number generator. We're just going to do 50 iterations again, and we'll go 30 time steps again to keep things small. We said for our initial conditions, we're going to specify 50 nodes, and that these randomly chosen nodes are going to be in the infectious state. And so these are the 50 nodes from which the disease starts spreading. And Tanveer has added a number of codes to provide different ways to choose these seed nodes. And that also is going to be incorporated in the very near future. It's in the process. Dustin is driving that kind of work. So the output, we're just going to say sim raw data, and it's going to be P01, and the infectious duration is 3. And let's see, I've got the friendship network there, and I have to select the container. So before we set this up today, I just made a new directory here, and I'm going to put it in for these 3 different simulations. We want it to go in here for the probability of 0.1 and the duration of 3. So we're going to select that now that all the inputs have been specified, and we submit this job, and we get the green banner up at top, the transient banner that says the job was submitted successfully. So then this is one of my favorite parts of the whole system. This simulation that we just specified is queued, but we can use that double curved arrow. And now what we're doing is saying, okay, we're presented with the same input screen that we just filled out, but now we just want to change a couple of values and resubmit the next job. So this one is much faster than the previous job. So we want to make the infectious duration 1. This was one of our cases we talked about to see what that effect is. So I want to change it. So in the output, the duration is 1 day. And then I also want to come back here and do something different with the path and put it in the appropriate subdirectory that corresponds to the new infectious duration of 1. And now we're going to submit that job. So now we have 2 jobs. This one's running. This one's queued. We're going to come back here and copy this guy again. And now we're going to make this probability 0.5 instead of 0.1. So we're having the edge probability. And now we just have to come over. All of our initial conditions and specifying nodes, et cetera, are the same. And we want to change this to 0.5. And then we're going to correspondingly change this directory for the output to 0.5. And we're going to submit that. In the interim, while these things are running, let me go back to the slides. Okay, so here's where we went to the demo, and I'm going to go to the punchline here. This is descriptions of what we just did in specifying these 3 simulations. You can see there's a bunch of screen captures to lead you through different choices for other demos. But what we're going to come down to is this. What we're going to try to do is recreate this slide. So we see this 3219, that's the name of the friendship network. SIR is the name of the model. P is the edge probability for transmission of the virus. And the D, again, is the infectious duration. We see that this leftmost curve is our base case. When the infectious duration is reduced to 1/3 of its original value, so it's 1, this is what happens. The outbreak size goes way down from about 880 to about 300. And then if from the base case we hold the infectious duration the same, but we change the edge probability, reduce it by 50%, you see that the reduction in the outbreak size, this is the cumulative number of nodes in the infectious state as a function of time in all 3 plots. And we see this went down roughly by 1/3 because we were up around 900. Now we're here around 600. So pardon me, I should have said this at the beginning, but each of these plots, the axes are the same. And what we have on the x-axis is time. We can think of it in days. So this simulation runs for 30 days, although the data stops changing at about day 24. And this is the cumulative number of infections that occurs during these simulations, okay? And that's the main curve where the error bars take account of the 50 different simulation instances that we run. And because they're stochastic, they give us different results. So you're seeing the vertical bars as being plus or minus 1 standard deviation. So let's go back and see where we are here. And all of these jobs have completed. Okay, let's just look at one of these for a second and go to the output for it. And so this is, again, an example of an enhancement that was done. This was done by Dustin to make the output more readily available to the user. So what's going on here is that this is an overview of the simulation. The outputs are shown here. This is the raw data from the simulation. I'm not going to go into that in the interest of time. But the initial states file, this denotes what 50 nodes are specified as infectious at the beginning of each of the 50 runs per simulation. This output file is what we just looked at. And now what happens when a simulation runs is all of this post-processing happens automatically. So these data are extracted out because remember we said there were 3 major steps: run the simulation, extract particular data out of the simulation raw output file. That's these results right here. That's the second step, so that then we can plot the data. But Dustin has already done some of that here. So basically what we're doing is looking at counts as a function of time, like we've looked at in the previous plots. And so time is always on the x-axis. And the way it works is each different state is in a row. So this is the S state, the next row is the I state, the next row is the R state, the bottom row. And each column then represents a different type of plot. These first column is the number of nodes that newly transition into a state. The second column is the current number of nodes in that state, because you can think of the infectious state. Some nodes are coming from the S state into I, and then some nodes leave the I state and go into the R state. And then the third column is the cumulative infection. So let's just look at this top plot. What is it telling us? Well, it's saying basically that over 800 nodes, and there's 885 nodes in this graph, basically about all of them are initially in the S state. They're susceptible. That means they can get infected. All the nodes are susceptible except for the 50 nodes that we specify as infectious initially. But you see there's 50 different curves here. In each plot, there's 50 different curves, one for each iteration we ran, and we specified 50 iterations. So what this is telling you then for this particular simulation is that the number of susceptible nodes over time gets driven down very close to 0. So by 10 days, the number of susceptible nodes remaining is approaching 0, which means that a lot of the nodes are becoming infected. And you see then this result over here, because the state I, the infectious state, the cumulative number of nodes that become infectious for all 50 iterations is up over 800 nodes. So it's almost all the nodes in the graph. So the point is, with these plots that are automatically generated, you can get insights into what the code is doing. And of course, you always want to be able to explain what the computations are instead of just taking them as on face value that they're correct. So what we're going to do then is we're going to run another job and we're going to plot one of these results up. Okay, so I'm just going to take this one here. So we're going to do a plot job. And so this is CSonnet again. And now we did data. This data analysis is what we can do by hand. But again, Dustin has it set up so this data analysis is already run once the simulation is complete. So the user doesn't have to submit these jobs. But what we're interested in is plotting something now. Okay, we're going to look at the plot and we're just going to take this baseline case and we're going to go into the raw simulation data. And so we're going to look at the infectious state, the cumulative number of infections. That's what we're going to plot. We're going to do error bar plot, line plot, scatter plot. Bar plot doesn't make much sense, so we're not going to do that. We can show the data points. Sure, why not? The output type, PDF, PNG, etc. We'll just say PDF. The output name, it's going to be the plot for the sim, where it's P of 0, 1 and D of 3. And we're going to put this into the appropriate container, our baseline case here. Okay, and then we're going to specify the legend. We'll just say this is going to be state I. And the color will just say it's going to be magenta so we can match that other slide. Now the title, I'm not going to put a title down, so I'm going to leave the text empty. On the x-axis, we're going to say, okay, the font size is 25. The x-axis text is, we're going to say time in days. The scale is going to be linear. What we're trying to do is reproduce one of the plots we saw on the slide. So on the x-axis, we're going to go from 0 to 30 days in increments of 10. And then the Y scale, we're going to do analogous set of specifications. We're going to just say cum, num, infected. And the Y scale will be linear. We're going to set the limits from 0 to 1,000. And we're going to do Y increment of 200. And the tick section, the font size, we're going to make it 25, consistent with the X and Y label font size. Axis scientific, I'm just going to put down neither for now. And now I'm going to submit this. Now, this screen, it's kind of tedious. There's a trade-off here. What we want to do is enable users to generate publication quality plots. But in order to do that, you have to have a lot of fields at the user's disposal that they can specify for themselves so they can customize the plot the way they want to. If we do a copy of this and we instead look at this situation where now the infectious duration is reduced to 1 day rather than 3, we just need to grab the appropriate data analysis output file. We change the output file name and we specify the container because we want it to be put in the container associated with the simulation. So data of one type are all in one directory. But then all of this doesn't have to change. So we've changed just a couple of inputs. Now we can submit the next job. And we'll see then if the first plotting job is completed in just a minute, the output here. So there's 3 different types of plots. This error bar plot, if we go to the data here, this plot here is this plot here, okay? And similarly, let's see if we can get lucky and go back to the jobs and see if this other guy is done. It is done, so that's a good thing. So we go to the output on the right. This is nice to jump around between inputs and outputs the way Dustin described in the first segment of the talk. And now the error bar plots. If we look at the data, this fellow right here, this curve, is this guy here, okay? One of the things I'd like to mention is that right now, the types of data plots we have are simply time histories, and they're very useful because they're close to the raw data. So you always want to look at these to make sure that what's going on is physically meaningful, it makes sense, etc. But there's all different kinds of plots that we generate to do this type of work for papers and to look at special information or special cases that we're running simulations on. And so if there's anyone in the audience doing simulations and they are generating plot codes to display data in different ways, if you want to, you can contact us as you go forward, and maybe we can integrate your code into this Net.Science cyber infrastructure. With that, we'll end, but I'll just come back to this beginning here. In the About screen, this gives a vision of Net.Science, but also we're not doing this work alone. There's a number of different institutions that are working with us on this project. You can see them here. Indiana University, these folks have moved over to UVA, but there's Jackson State, North Carolina A&T, Stanford, Virginia Tech, Los Alamos, Kitware, Network Repository. So all these different folks are helping us do this work. And if you have questions or comments or codes that you think we might be interested in to integrate into the system, under About, you always have the contact, and you can send us an email at net.science@virginia.edu.